All right, welcome back. So in this video, we're going to talk about some specifics about those crystalline solids. So remember in that last video, I drew the little graphic organizer where you have solids and it's broken up into crystalline and amorphous solids. And then the crystalline solids were broken up into further categories of ionic, molecular, and atomic solids. And then atomic solids were broken down even further into metallic, network covalent, and then group 8A. And so we're going to, in this video, begin talking about this whole side of the graphic organizer. So looking at the crystalline solids and then the different types of crystalline solids. So remember, we're talking about those types of solids that have the highly ordered arrangement of particles. And so, for example, the ions in an ionic compound are very orderly. And so we're looking at specifically the 3D lattices is what's going to differentiate the ionic from the molecular from the atomic solids. But here, let me define them for you. So an ionic solid is the first one we're going to talk about. Ionic solids have ions at the points of the lattice, and that's what describes the structure of the solid. And so, for example, if we look at table salt, sodium chloride, it's an ionic solid. And at those lattice points, at the little corners of each of the boxes in the previous video that I showed you, are sodium ions or chlorine ions. And that just goes in a organized repeating pattern that creates the lattice of an ionic solid. The next one is a molecular solid. Molecular solids have discrete covalently bonded molecules at each of its lattice points. And so instead of having ions like the ionic solids, they have molecules. So for example, if we look at an ice cube, at each one of those lattice points is going to be a water molecule. And there's a picture on the next slide to show you what exactly this looks like. And finally, the final category of crystalline solids are atomic solids. And so atomic solids have atoms at the lattice points. One example of carbon, as maybe you're familiar with the term allotrope, so different forms of the same atom or the same compound. And so allotropes of carbon exist as graphite and diamond. So both molecularly, graphite and diamond are both just carbon, but the atoms are arranged differently. And specifically, those atoms are carbon, and they're all just carbon atoms repeating in an organized way. And so that's what creates an atomic solid. And so here is a picture to show you what it is that I'm talking about. And so this first picture on the left, you have each one of these gray circles, which represents here carbon. And so if we have carbon, 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 each one of these carbon atoms is a lattice point. And so if it's just a bunch of carbon atoms, that makes this an atomic solid. And this specifically is diamond. So this is what the structure of a diamond molecule looks like. The next one here in the middle, B, each one of these gray or white and green circles are different ions. So you have a chlorine ion, a sodium ion, a chlorine ion, sodium chloride. And so each one of these lattice points are ions, making B, this middle picture, an ionic solid. And finally, this is what ice looks like. And so you have each one of these right here. Let me find one that's a little bit easier to see. This one here. This is a lattice point right here, and this is a lattice point right here. This is a lattice point right here, and so each of these that I've circled is a lattice point, specifically H2O, and so each of these are molecules, and so this is a molecular solid. And so that's the difference between an atomic solid that has atoms at its lattice points, an ionic solid that has ions at its lattice points, and a molecular solid that have molecules at its lattice point. Okay, before we go into more detail about atomic solids, I'm going to go through some specific characteristics of molecular and ionic solids that you should be familiar with. And we did talk about these in Chem 1, so hopefully this is a review for you. And then we'll go into more detail about the atomic solids that are new for you. And so some characteristics for molecular solids that you should know: they have strong covalent bonding within the molecules. So the things that are holding the atoms together are very strong covalent bonds. But then the attraction between the molecules are pretty weak. Those are the weak IMFs that are holding it together. And so just as a way to reinforce this idea of the weak forces between the molecules, it requires less energy to break the intermolecular forces, and because of that, they're going to have lower melting points compared to an ionic solid, which we'll talk about in a moment. For the other part of the molecular solids that you should be familiar with is the question: would you expect a molecular solid that is nonpolar to be a gas or a solid or a liquid at room temperature? And if you're looking at small molecules, we would expect that to be a gas at room temperature. However, if you have a larger molecule, we would expect those to be liquids or solids at room temperature. And this just goes for molecular solids. And again, because of an increasing of dispersion forces, and that's the whole reason behind this. Finally, some characteristics of ionic solids that you should know and hopefully remember from Chem 1 is they are very stable. Because they are stable, they're going to have very high melting points. And this high melting point specifically is as a result of the strong electrostatic attraction. And electrostatic attraction just means the attraction between oppositely charged ions. So electrostatic is just a fancy way for saying oppositely charged ions. And that's what's holding an ionic solid together. The difference between intermolecular forces and interionic forces, that intermolecular forces are typically weak. And so these intermolecular forces, those would be your London dispersion, your dipole-dipole, and your hydrogen bonding. Relatively weak. Typically, they are much weaker than the interionic ones. And the interionic forces are going to be relatively strong. And this just goes back into explaining why ionic solids have such strong or such high melting points. How does this affect the boiling and melting point? I just said that. And so if you look at something like an intermolecular force, those London dispersion, dipole-dipole, hydrogen bonding, because they are relatively weak, you're going to have a relatively low boiling and melting point for whatever substance you're talking about. Whereas if you're looking at something that has interionic attraction, because that interionic attraction is so strong and that molecule is so stable, they are going to have very high melting and boiling points. Think about the idea of taking some salt and trying to melt it in a pan on your stove. It's going to be very difficult to do that because salt is held together by that interionic attraction, which is going to be very strong, and it's going to require incredible amounts of energy in order to break that attraction. So hopefully none of that is new, and that's a review from what we did in Chem 1. If not, as it says back here, in the previous slide, you can reference those two sections. I believe it's sections 5 and 6 of chapter 11 in your textbook if you would like some more information about that. The last part of this video that I'm going to go through, and we'll do some more with atomic solids in class, is I just want to briefly give you an overview of the different types of atomic solids. And so the first one that we're going to talk about are molecular solids. Molecular solids are a special type of delocalized non-directional covalent bonding. Oh, what does that mean? So delocalized means that you don't exactly know where the electrons are. You can't pinpoint exactly where the electrons are. They're delocalized. They don't have a specific location. Non-directional covalent bond. And we say that they're covalent because the different metal atoms are all sharing this collection of delocalized electrons. And so we say that they're covalent because the electrons among all metal atoms. Now we'll talk more about that in class, but just to give you a picture of what I mean by this. And so this picture is a little bit of a example of what a metallic solid looks like. And so each one of these electrons, they're delocalized, they're not in specific locations that move around, but all these electrons are being shared among all of the metal atoms. And so that's why we say that they're covalent bonds. Let's go back here. Okay, the next type are network solids, sometimes called network covalent solids. And in a network covalent solid, the atoms are bonded together with strong directional covalent bonds that lead to giant molecules or networks of atoms. And so the important thing to notice between the two of these, and we'll look more at it in class, but the difference, not only are the network solids going to be quite a bit larger, but a metallic solid is going to have a non-directional covalent bonds. And so there's not a specific direction, there's not a specific angle in which these electrons are shared, whereas in a network solid, they have strong directional covalent bonds. And so they're going to have specific angles, they're going to be very rigid angles, and that's going to help you differentiate between the properties of a metallic solid and a network solid. And again, we'll talk about a network solids quite a bit in class, but just as a little key, if you see carbon or you see silicon in the solid, it's probably going to be a network solid. Those are two very important atoms that make up any type of network covalent solid or just network solid. And the final type of atomic solid that we really won't talk about a whole lot because, to be honest, it doesn't really have any purpose. They don't exist very often, but they're group 8A solids. And so this would be if you took the noble gases, which are group 8A, and made them into a solid, they would fall under that group 8A. Now, they have really no practical purpose. It's very difficult to make a noble gas into a solid. But if you were to, under the specific conditions, you'd have a group 8A solid. But again, we're not going to talk very much about it at all because they have really no practical purpose and there's not really any need for them to be a solid. And so they serve their purpose as being a gas. And so we're really not going to focus too much of our attention on that, but it is important that you know that they do exist. This table here, and there's a similar table later on in the notes that we'll talk about, but this table is a summary of the type of solids that we talked about. And so I would recommend that you either copy this in your notes or just take a look at it. It's very important for you to know the specific things in this chart for a test or a quiz, and also for the AP exam. This picture is the final picture that we're going to talk about in this video. And again, it just shows you the different type of solids. And so if you look at this first one on the left, it's a metallic solid. So it's extended network of atoms held together by metallic bonding. So that sea of electrons, each one of these gray things are a different atom. So maybe you have a bunch of copper or a bunch of iron. Atomic solids are the next one here, and it's an extended network of ions held together by the ion-ion interactions. And so each one of these circles is a different ion. So maybe you have a magnesium ion and an oxygen ion, and then a magnesium ion and an oxygen ion. That's an atomic solid. The one below here is a molecular solids, and so they are discrete molecules held together by those intermolecular forces. And so there's a water molecule held together by hydrogen bonding to another water molecule, and that's sort of a picture of what a molecular solid looks like. And finally, in the bottom left corner is an example of a network covalent or a covalent network solid, and it's an extended network of atoms held together by those strong directional covalent bonds. And as I mentioned a moment ago, when you see carbon or silicon in some sort of solid, it's probably going to be a network covalent solid, and we'll talk more about that again in class. And that's it for the brief overview of the different types of solids, or specifically the crystalline solids.